we make what claim did we just make? What claim did we just make?
We're 95% certain.
We're 95% certain that secondhand smoke decreases lung function. So in other words, we said, yes, secondhand smoke is bad. The way we could be wrong is, we said secondhand smoke decreased lung function, when in fact, maybe it either increased lung function or it stayed the same. So in other words, it could be that this null curve right here is the correct curve, and we happen to land, as Caitlin said, in the outlier region of it. Remember the breast cancer curve from yesterday? Let me mute the screen for just a second. I want to draw something on that. The breast cancer curve yesterday, there was the breast cancer curve of those that didn't drink green tea. Remember the second curve I added yesterday? I added a second curve onto it, kind of down here. And I said, that's the curve of those drinking green tea. And I asked, we can't prove which curve this point lies on. We can't prove which one it lies on. But which one is it more likely to lie on? Blue or orange? It's more likely to lie on orange, which means, same exact argument here. This orange curve here, take 5% out. This orange curve here is a more likely living place for that data point. It doesn't prove that it can't be on this curve. It just shows that it's more likely it's on this curve. But we could be wrong. Even though it's more likely, certain times it's going to be on this curve. You'll study this in your project for next week, which is a closer look at confidence. You'll see that every once in a while, your intervals miss. You set up the interval, and you miss the interval due to randomness, not due to poor experimentation, but just it's 95% confidence. Paris, go ahead.
Okay, so let's say you got your data and it was really close to like being outside of
That's a great question.
the margin.
Great question.
Brought you over, what would it be?
This is a fantastic question. I want to answer it 3 different ways. Paris asked a great question. Suppose, let's get this guy out of here, shall we? So suppose, there's the cutoff right there. There's the cutoff, the Z. This is called a critical value. Put that in the back of your mind. We'll come back to that today. So it's obviously pretty clear what our decision is going to be if our data lands like over here. Like, okay, that's pretty much normal. We were expecting nothing interesting happened. It's also fairly obvious if the data point lands like over here. Okay, that's pretty far away from what we were expecting. But what if it lands like right there? What if it lands right there? What do we do? Now, first of all, I'm going to answer it the first way by saying in this class, I will find you data sets that don't do that. Okay? So promise. I'm not going to hand you p-values that are 0.49993 and then dock you for rounding. That's BS. Actually, I take that back. 0.49993 would be easy to round. It rounds to 0.5, which would be right here. 0.04999993. And but what happens in reality? You're running your own study, and you land right here.
Rerun the study.
Tell me that again. Who said that? Susie, why would that be good?
Because you can tell if you're still at the same point or if it moves either way.
What's going to happen to this curve? Assuming the data behaves exactly the same way, assuming that it behaves exactly the same way in the second study, actually.
It's going to make it seem like that data does belong to that curve.
What's going to happen to this curve as our sample size increases?
It's going to get higher.
Up, and it's also going to do what? If it goes up, it has to do this, right? So what's going to happen, let me grab purple, because I think purple's close enough to blue. Suppose you double the study, do it a second time, and the data stays exactly where it stayed. So we got the exact same result, same average, essentially the same standard deviation in the sample. That might seem like you did the exact same study 2 times and got the same results, therefore you learn nothing. You actually learn quite a bit, because what that means is your sampling distribution is now going to do this, which means your 95% cutoff is now going to be somewhere over here to trap 95% of this area. But look at where your test statistic landed. It still landed over here, which is now well out there in that called rejection region. Does that make sense? So the quick and easy answer is go back and get more data and see what happens. Now this is also an expensive response sometimes, but it's the best response. There was an article just written up about this, about the Amanda Knox case. I think Jared mentioned it in class last time. Same exact thing. If you run a study twice and get similar results that are both close to inconclusive, pull them together. You've heard of replicating studies? That's the whole point of a replication of a study. If you can replicate it, you can pull all those results, assuming these studies were done exactly the same way. I'm making a lot of assumptions here. But this is what would happen, most likely, Paris. Now, we're also assuming that it stays right there. It might be that you got one of those 5% flukes, and you run the study, or colleagues run the study, and they all end up over here. And then you say, well, I got the fluke. I got the fluke. I got my type 1 error. We'll come back to what that means in a second. that a good answer? And the third way of answering it is actually involved in your homework, I think in either this homework set or the next homework set, where I kind of walk you through what to do, like more analytically. Cool, great question. That's a fantastic question. Please don't sweat it like on an in-class assessment in here or even out of class. I find you nice data sets that behave obviously as to which side they fall on. But in reality, sometimes they don't, and that's important to know. Good, very good question. Any other questions on that before we move on? That's great. All right, let's analyze now. Let's analyze. 1 hour has passed. We've taken the cigarettes away. Have you guys noticed the e-cigarettes around town? People smoking those. They freak me out. Like I'm at a punk show and there's a dude smoking right next to me like, you son of a... I'm like, what? Just feels like warm air. I don't smell anything. It's kind of, yeah, so kind of freakish. They suck in it with little LED lights up. Like it's actually a cigarette. It's quite interesting.
They're running tests on those to see if the air that they're...
Yeah, they're not.
Is more than just carbon
They're
dioxide?
not thinking that it's healthy now.
Oh, interesting. But there's no smoke.
Yeah, but it's...
So there's something else besides the smoke.
Yeah.
There's nicotine in there.
Right, but is that being exhaled? Nah, that's a study. There's a study. They're trying to see if the nicotine is actually going out into the right. Does nicotine get exhaled in normal cigarettes? I don't know the answer to this.
Yeah, I don't mean.
Yeah, I don't know.
Well, it gets in your blood system, so it must.
But that's you, not, see, that I would imagine that you're concerned about those around you, because that's the whole point of
Right.
smoking in public, is that it's not just affecting you, it's affecting everyone. Smoking is such a unique thing, right? Because it's not like listening to loud music, like, "Argh!" You can put headphones on and not bother those around you. When you smoke, you're like, but all of a sudden everybody within a 10-foot radius is affected by you directly.
I can't think that nicotine would, because it's addictive. So the people that would be ingesting the secondhand smoke would find some kind of, they would get some high off of it. I've never known anything.
Maybe that's what we're studying. Maybe they're placing some kind of a precision measurement on these, basically this study, but with e-cigarettes and nicotine, or some other, who knows. I'd love to see that study.
Yeah, but they've already showed that, like, if
I
parents
just
smoke
read
it
it
around their
in the
kids,
bulletin the other
the
day.
odds are that they're gonna grow up and smoke, and I've read.
Smoking.
Well, I've read a study, though, that, it's because of the nicotine.
Oh, so maybe it had
They
just
eat
one
cold
study?
and they need it.
Is it just
Yeah,
one?
just a long time ago.
Well, that's the thing. I love to see these replicated because I've heard the exact same thing that secondhand smoke is just as damaging as smoking
And plus,
itself.
you're more likely to grow up and smoke if you're around it.
Sure.
You know.
So you're slowly debilitating some
How
lung
much that's
functions.
psychological though versus like physiological?
Yeah. That's tricky.
Psychological practice is seeing
Yeah.
people around
Yes, yes. Modeling behavior. Yes. That's trickier, right? See, now you guys hit the nail on the head here. Psychological versus a measurement model. Those always get crushed more critically than a measurement model. Because it's like a psych model, measuring that kind of a thing is trickier to do than measuring, say, a lung function. Sticking a tube in somebody's lung and measuring how much air it takes is easy to do. The criticism of that, of course, is what you're measuring actually implying what you're able to study. That's another so it's interesting. That's why the design of experiments is so important and why you have entire classes devoted to it, right? I almost wish you had your design experiment class before you came here, but that's not the way it works, I guess, yet. Give me 20 years, I'll fix that. 20 years. That might take that long. So anyway, we're back to here now. Let me slide this bad boy up. We're gonna start from scratch with this again. All right, so here we go. 3 hours, they were at baseline levels. What are our Nolan research hypotheses? It's a bit of a trick question. They're exactly the same. We're still trying to see, at 3 hours, if lung function has been decreased, or if it has not been decreased. We're trying to see which one of these two things, one of them is going to be true. Our job is to decide which one it is. So my question for you is, which one do we believe? Which one of these do we believe? Based only on what I've got in red up there on the screen. Susie?
Well, I had a question first.
Oh, go ahead, question first.
So don't you kind of switch them?
You can switch them, but again, I'm not going to, because what curve is easier for us to draw? This one. We know what baseline was, so we still know. You can, of course you can, but we know what baseline was. Baseline was here, and we know that this down here at 5%, wherever that is, whatever that Bob per liter measurement is. Sorry, Bob, didn't mean to invent a unit for you. So whatever this is too far down to be decreased, and then we've got the null curve. So Susie, I'd rather not switch it. I'd rather create, and basically the curve's going to be the same as it was before. Well, my question for you, Georgiana.
But now it's gonna be greater than 5%.
So where did we land, friend?
It's gonna be in the blue.
And we landed in the blue, didn't we?
Yeah.
We don't exactly know where, but all that matters is we landed somewhere in it. So since we landed in the blue, that means we landed where we thought we were going to land. We didn't land down here, which would have supported this guy right here. So who do we support? We support that lung function has not been decreased after 3 hours, which is exactly what it says. At 3 hours, they were at baseline. They recovered back to baseline. So we'll pull this down because I have the statement on the next slide, I think. If I was watching how to put this together. Yes, there's the conditional. So after 3 hours, we were expecting secondhand smoke to have no lowering effect after 3 hours. And guess what happened? There was no lowered lung effect after 3 hours. So does this piece agree with this piece? They agree with each other, and that's why the probability is bigger than 5%. Bigger than 5% means they agree. So does it appear, secondhand smoke appear to affect lung function after 3 hours? No, it doesn't. It appears that after 3 hours, your lungs have flushed everything out that was the bother from 0 to 1. Actually, go.
I was just thinking about what you said earlier about adding and looking at that statement.
Yes.
So if we're looking at that, could we say that like each one of those is 2.5%?
Well, the 2.5 actually is implying back to the 2.5, 2.5%. Let me go back to this curve over here. Let me shut this down for a sec. I love what you're saying. So the only time you'd put a 2.5 here and a 2.5 here is if you were just trying to see if there was a change in something. Not a directional change, but just an overall change. So did it either go up or go down? Here, we want to actually show it went down. So we're putting all the area on one side.
Right. But I was just looking at the statement, sorry, it's probably confusing.
Oh, gotcha. Since they're using the word decreased.
And adding those two probabilities greater than 5%, we,
I'm not following you now. I'm sorry.
I don't.
So you're saying you'd rather this be 2.5 and 2.5?
No.
No, you would rather that.
I was looking at the statement and the little line means you're adding those two.
Oh, you're not talking about this at all. You're talking about this statement. I got you. I see now. I see. I got it. That right there.
Yeah.
What does that mean?
If those conditions.
If these conditions are met, what's the chance we got this? So in other words, this is the unknown, this is the assumption. So we're assuming, given that, secondhand smoke had no lowering effect on lung function after 3 hours, what's the chance that we got non-lowered data? Well, if we were expecting non-lowered data, and we got non-lowered data, that means there's agreement, which means we landed in the confidence interval we built. That's why it's so large. It's large because we got what we were expecting to get. Therefore, no contradiction. Therefore, we believe, the ones in the other rooms have brakes on them that slow them down from doing that. Holy hell. That's why we knock out Sean. Well, almost a break anyway. That'd be kind of a fun way to start a break. We believe this up here. We believe this up here because this is that blue interval, essentially. Cool. Is that? I understand what you're saying. Actually, love what you're saying. Now, going back to what Paris said, right? We could run this study again. Same conditions, same constraints. Maybe we'd even land in the same place data-wise. Maybe. What would happen to the curve? It's going to pull up and pull up and pull up. So that data point is going to get more extreme, assuming it stays put, because as the curves get up, just by definition of staying there, it's actually becoming more of an outlier to either side, because the tails are squishing down and the curves are getting taller. So don't ever forget that that's in the background. That central limit theorem is still back there. We'll come back to that again and again and again. Christian, go!
So, both parts of it show that secondhand smoke does not decrease lung function.
When you say both parts,
The 0 to 1 hour and the...
what do you guys say to that?
No, the first part is
The
yes.
first part, it does show. It does decrease, right?
Okay.
Because the p-value was, which means we're out of the blue interval. The blue interval says lung function's the same as it was or even got better. This says we're not there. This says we've gotten worse. This says we're in the it's as good as it was or it got better.
Okay.
You see?
And if that percent represents data points, but it's not.
Good. I'm hiding the data from you right now, Christian. I'm hiding the data. We're going to get to the data after break, I promise you. But right now, I just want to focus on that percentage. And I love the questions I'm getting. And this gives me reason to keep doing this extra bit, because I want to make sure that's solid when we get into it. Cool? Very good, very good, very good. Could we be, oh, Karen, go ahead.
Well, I was just gonna say in answer to his question.
Yes, please.
The way that I wrote it down is secondhand smoke does cause lung function for women. The answer is yes, because secondhand smoke could cause lung function to increase or stay the same.
Good, that's totally fine.
Say that differently.
There are there's formal and informal ways of saying this, and the way I've got this set up too, you'll see it later on. I have a bit of a template for you guys to walk through when you're first learning how to write your conclusions. The conclusion is the most important part. So the very formal way is you say, I would, so we're talking about this one right here, right, Karen? At 3 hours?
No, the first one.
So this one up here, at 0 to 1 hour? Let's just go here if
Because
you
you
would.
asked how could we be wrong? Could we be wrong in the first one? Yes.
Yeah, we could be wrong for this one too.
Yeah.
By 5%.
Actually, no. This is, no, this is tricky. This is tricky. We'll come back to this. It's not, that. How could you be wrong here? We made the conclusion that lung function is not decreasing, that secondhand smoke is not decreasing lung function after 3 hours. Could we be wrong? Yes, it might be decreasing lung function, but we missed it. You see the difference between this and the first one? In the first one, we said it's being decreased when maybe it's not. In this one, we're saying it's not being decreased when in fact it might be. The first is a false positive. This one right here would be a false negative. They're trickier to measure. We'll come back to that, Georgiana, in like weeks, seriously. Yeah, a false positive, the rate of false positives for our test is always going to be 5%, because that's the size of the tail we built. The trick with false negatives is there's another curve in there that we haven't talked about yet. He's floating around. He's floating around. He might be close, he might be far. We'll come back to him, I promise. After break, let's take our 5, yes? Because I want to get back into this false positive, false negative talk. And I want to talk again to Georgiana about why it's not 5%. Necessarily, it could be, not necessarily 5%.